Good afternoon, everybody. Welcome to Wednesday sunny afternoon of Chem 170 with your host, me, Dr. White. Now, I think I said today I would go through first, I got to open it up first, the esters and carboxylic acid problem set. So I better open it up. That's not the one I want. That's the one I want. And let me just do one more thing. Hang in there. I always use that expression. Well, it works. All right. Now I know where I should be. All right, let's get started. Everybody say carboxylic acids ester problem set. Thank you. All right. On test number 3, which is coming up in the near future, and I believe it's after next week. But it'll be similar to like test number 2. There'll be nomenclature problems, reactions, and general knowledge. Speaking about general knowledge, did anybody happen to pick up a bottle of vinegar and look at it and say, oh, that's got acetic acid, a carboxylic acid? Did you do that? Did you pick up a bottle of mustard or ketchup or relish and see it's got vinegar, which you know has acetic acid, which is a carboxylic acid? Did you think about that? Or how about if you were removing nail polish and you looked at the bottle and said ethyl acetate, which is an ester, which is found in one type of nail polish remover. Remember, organic chemistry is all around you, and it won't hurt for you to think about it. Oh, I can add one more to the list. Do you happen to use a fabric softener and think that's a quaternary ammonium salt? You should. And those are near and dear to my heart because they help pay for my mortgage and a couple of cars too. All right, let's get going. All right, nomenclature questions. You know there are 2 types. Type 1, here's the structure, give the IUPAC name. Type 2, here's the name, draw the structure. Let's do type 1. Give the IUPAC name for the following. Look for what's different, what's not carbon, what's not hydrogen, to get your attention like that. And if we look at A, we have a carbonyl hydroxy group R group carboxylic acid. Find the longest chain with the carbonyl carbon double bond to oxygen. That's always carbon 1, so you don't have to put that down. And you name it as an alkane, butane, drop the E, add OIC in the word acid, and you get butanoic acid. Now B, when R is a benzene ring, this is the common name that IUPAC made also the IUPAC name, and that's benzoic acid. And let's skip to E. And E, what do we have? Carbonyl hydroxy group, R group. It's a carboxylic acid. What's the longest chain, including the carbonyl carbon? 9. That's no name. Drop the E, add OIC in the word acid, nonoic acid. Now, we've got alkyl substituents. And notice on carbon number 4, I have an isopropyl group, or you have an isopropyl group. And on carbon 7, there's an ethyl group. And therefore, it would be 7-ethyl-4-isopropyl nonoic acid. Say that 5 times quickly. However, since I am not holding you to the IUPAC alphabet rule for substituents, if you had put down 4-isopropyl 7-ethyl nonoic acid, I would mark it correct, even though the IUPAC police would arrest me for doing that. No, they won't. But anyways, let's look at F and G. And what's different? Carbonyl with an oxygen minus and a cation, in this case sodium. This is a carboxylate anion. How do you name a carboxylate anion? Similar to an ester, which we'll cover, the cation you name in the front as the element it is, sodium. When R is carbons, which it is, find the longest chain, 3, drop the E of the alkane name and add OATE. So that'll be sodium propanoate. Now, when R is benzene ring, you can't use it. So you have to use the IUPAC method. This comes from, first of all, it's again carboxylate anion. Name the element that the cation is in front, potassium. And this comes from benzoic acid. Drop the IC and the word acid from benzoic and add ATE, and this is potassium benzoate. Now here we have an ester. And how do you do an ester? Well, the R carbons on the oxygen, R prime, you name as front as a alkyl group, ethyl. And then when this is all non-aromatic, the student I had who came up with a better method than IUPAC for this, even though you really can't use this for IUPAC all the time, is find how many carbons, 3, longest chain with the carbonyl carbon, drop the E of the alkane name pentane, add OATE. And that would be ethyl propanoate. Now, when this is a benzene ring, you have to use the IUPAC method. And that is name the alkyl group on O, the oxygen, as the alkyl group it is in front. Then if that were an H, benzoic acid, drop the IC in the word acid and add ATE, and you get methyl benzoate. Remember my promise to you for esters and carboxylate anions on the R group. I will not give a substituent there. Gets real messy, real messy. Here, let me, anyways. All right, the other type of nomenclature problem, draw the condensed structure for the following organic molecules. And there's some common names I asked you to know. Acetic acid, remember that's in vinegar, is the simplest carboxylic acid where R is a methyl. If we look at C, 2-ethylhexanoic acid, which is a very evil molecule, because it gave me about 6 weeks of grief until I found it was an impurity in an aldehyde I was using for a new reaction that we were ready to go to the plant, but we found this impurity. Well, it took a while to find it. It messed things up. But anyways, how do you name this? Start from the right, move left. Hexanoic acid, carboxylic acid. If OIC was an E, hexane, 6 carbons. On carbon 2, remember the carbonyl carbon is 1, we have an ethyl group. Oh, everybody, heads up. Everybody, G, cross off, I violated my promise to you. That will never be on a test or the final. All right, let's look at F. How do you draw this molecule? OAT ending, either an ester or carboxylate anion. If you look in the front, if it's an R group, ethyl, it's an ester. And how many carbons, including the carbonyl carbon here, propane, if you drop the OAT, 3, and this is how you draw the ester. Now, The other common name I asked was, you should know, ethyl acetate, like you find in nail polish remover, is this ester. Nobody ever calls it ethyl ethanoate because everybody uses the common name. It's been around a lot longer. Now, I see a mistake again. J, magnesium acetate, cross off. I thought I got them all. I missed this one. Sorry. J, just cross off. I'm going to stick to the alkali metals, lithium, sodium, and potassium for carboxylate anions. Even though this is the correct name and valid, I just won't have it in our class. All right, let's look at draw the condensed structure for the following reactions. And what you have to do is identify what's different. In this one, aldehyde, O bracket O, oxidize, and you oxidize an aldehyde to a carboxylic acid. And here R is methyl, and we get acetic acid. And if you look at D, what have I done? I've done the standard trick an organic chemistry instructor does on a test. Put a big, scary R group. But if you've been paying attention, and I hope you have, you look for what's different, what's not carbon, what's not hydrogen. To get your attention like that, oxygen, carbonyl, hydrogen, R group, aldehyde, oxidize it. Everything comes along for the ride. Because do you break carbon-carbon single bonds? No. And then this becomes a carboxylic acid. Now, next reaction is really cool. Why? Because you use dry ice a lot of times when you do this, which is really cool. And here, what do we have that's different? Magnesium bromide on a carbon, Grignard reagent, CO2, second step, acid and water. And you get a carboxylic acid that's one carbon longer than the R group you started with. Here R is 2, and we now have 3 in the carboxylic acid counting the carbonyl carbon. And if we look at A, I've done the same standard trick, big, scary R group, but if you look for what's different, here's Grignard, CO2. This long thing is just an R group. You tack a carbonyl, OH on the end here, and you get a carboxylic acid that's one carbon longer than the carbon R group you started with in the Grignard. Remember, your friend on every test in the final will be, do you break carbon-carbon single bonds? No. And there's 4 bonds to carbon. All right, let's go to B. And in B, what do we have? Carboxylic acid reacting. I could have had water underneath there. I should have, sorry. But anyways, you can actually do solid state too, which is what this is, but never mind. And here M, I didn't put down there, can be lithium, sodium, or potassium. Is sodium, you get the carboxylate anion, and R is this. It comes along for the ride. The only thing that changes, OH becomes O minus, Na plus. Remember, you do not have to put charges. You could have put O, Na, even though I always will. And I give you a couple more examples. All right, everybody, pay attention. Number 5. This is a different problem that I normally do for reactions. And here it says, draw the condensed structures for all the products, not just the organic, but all of them. And if we look at what do we have? We have, a carboxylic acid and NaHCO3, sodium bicarbonate, and this is a base, this is an acid, and you form the carboxylate anion. But as I'm taught in class, the sodium bicarbonate becomes carbonic acid, which faster than I can clap or even think, breaks down to CO2. The RF tells you it's given off as a gas, and water. And I have a few more. All right, made a mistake again. 6A, cross off. It's correct, but I don't do divalent bases like that or cations for this class. Same thing for B. Sorry about that. Ooh, quick question while we have sodium bicarbonate on the board. Anybody happen to try my father's method for making better spaghetti sauce by putting some sodium bicarbonate at the very end of your spaghetti sauce? Because the citric acid, a carboxylic acid, is neutralized and the pH goes up. And if you do it and look in the pot, you'll see some bubbles and foam, and that's from the carbon dioxide that's formed when the carbonic acid breaks down to water and CO2. How do you like that? Breaks down. That's my new special breaks down effect. Nah, not really. Or, did anybody remember the little rocket ship that had the awful candy in it, but you used it as a tube with a cap, put vinegar, baking powder, slam the cap on it, hold it, builds up CO2 and goes boom. Oh, I have a fond memory of that. My father taught me when I was very young a lot of cool chemistry stuff. I wonder why I became a chemist. All right, let's continue on. There's a lot to do in this problem set. Well, there's a lot I talked about. All right, let's look at C. What would be the organic product or products for a following reaction? And here again, you have to play that fun game, and we'll probably play that maybe Monday again. Circle and name the functional groups. Well, you don't have to circle them, but you have to identify them. And the first one, carbonyl, hydroxy group, R group, carboxylic acid. Second one, carbon, hydroxyl group, alcohol. Acid catalyst, H plus. Carboxylic acid, alcohol, ester. And what's my R group? 3 carbons. What's my R prime? 1. And that's the ester you get. And if you look at D, this is important. We have a carboxylic acid and alcohol acid plus H plus catalyst, and we'll make an ester. And the carbon in R prime with the hydroxyl group is the, carbon in the R prime of the actual ester with the oxygen. So this carbon here is this carbon here, and that's why it has that oxygen in there. And I give you a bunch of more examples where I have different R groups in R prime. But what I've been training you to do, which is the beauty, the power of organic chemistry, even though you're dealing with different molecules, like if you look at D and F or E, D and E, those are different carboxylic acids, but they're both carboxylic acids. Same thing with the alcohols. They're different alcohols, but the general reaction, this is the beauty of organic chemistry in my mind, but I'm biased, I'm a synthetic organic chemist, is any carboxylic acid, any alcohol, acid catalyst, you'll make an ester. All right, let's look at G. By the way, everybody see G on your screen? Thank you. Just checking. And what do we have? Well, we got a benzene ring, but a benzene ring won't react with sodium hydroxide and water. I forgot the water in the problem set. I wrote it in the answer set. And therefore, benzene won't react with it. But we have an ester, base, and water. you get back not the carboxylic acid you would have used to make that ester, but the carboxylate anion of that carboxylic acid. And why is that so? Because the carboxylic acid is acidic and in base forms a carboxylate anion, but you also get the alcohol. In this case, R is benzene ring, you get sodium you get sodium benzoate, and the R prime gives you methanol. Now, if you do the same reaction with acid, you'll get back the carboxylic acid and the alcohol you would have used to make that ester. And notice in B, I get fancy. And you got a big long R group, and R prime is a benzene ring. Guess what? Acid and water will not react with a benzene ring, but that's your R prime to form this alcohol, phenol. Now, when I wrote D, I was thinking like a general organic chemist who don't balance equations, but on the test, I'll put that 2 there. What do we have? We have an ester reacting with 2 moles of a Grignard, MgX, X can be chlorine, bromine, or iodine, and each R triple prime bonds to what was the carbonyl carbon. That R group is still there too, and the OR prime gets kicked out. I like that new kicked out. That was pretty lame. But anyways, kicked out to make this alcohol. And if we look here, what's R? It's attached to the carbonyl carbon, will still be attached to the carbon with the hydroxyl group. What's R prime, triple prime, methyl? And so that same carbon with the hydroxyl group, you get not 1, but 2 R groups. Can you people keep a secret? Can you keep a secret? Shh. Students have trouble with this on a test. Hint, students have trouble with this on a test. Hint. And if you notice, Dr. White had a lot of fun with E. Here, R is ethyl. We have an ester, Grignard. R prime, triple prime is pretty complex. By the way, that's called a sec-butyl group, which I didn't teach you. And here's the 2 alcohols, and the key alcohol is the first one. Look how complex that is. And with that, I'm done. Any questions about the carboxylic acid and ester problem set? Well, in that case, let's continue. Oh, I stopped. Hold on. Let's continue with, hold on, I'm looking what color my eyes today. I should put that on test. What color eyes are Dr. White? What matters what day it is? Because they go anywhere. What would you call them? Blue, green now to blue, depending on whatever. All right. Everybody see reduction of a nitrile on Monday. And I wanted to ask you that. Anybody notice anything different about Monday's video? I mean, I don't have a piece of food stuck in my beard or anything like that, because it's got 122 views. I'm not giving away the secrets to the United States in there like Trump does, am I? No. It shocked me. I know something I said there caught somebody's attention. All right, let's get back. We were talking about this reaction. You take a nitrile, carbon triple bond to nitrogen, hydrogen a catalyst, and you hydrogenate it, add hydrogen to catalyst, you'll get a primary amine. So we did some of these. Let's do two more. And your turn. What would be the product or products of the following reaction? And when you're done, give me a thumbs up. All right, I got to go. My turn. All right, look for what's different. Ooh, what's not carbon, what's not hydrogen, ooh, nitrogen, and what's not a carbon-carbon single bond, a triple bond. This is a nitrile. A triple bond. It's made up of 2 pi bonds and 1 sigma. And when you add hydrogen excess and nickel is a catalyst, remember the catalyst can be nickel, platinum, or palladium. And you break the 2 pi bonds and you get a primary amine, which you can also write like this. And on a test, either one would be correct. Well, what's my R group? 3 carbons. 1, 2, 3. Remember, you don't break carbon-carbon single bonds. Then I'll have this carbon here, which is this carbon, becomes this carbon, and then nitrogen, and each one has 4 hydrogens. And I know there are 4 bonds to carbon, so I can put in the rest of the hydrogens. Remember, that's your friend on every test. And that's how you do it. Now, let's do one more. On test 3, just like on test 2, I'll have 4 or 5 synthesis problems. And the question would be, what do you react with hydrogen excess and a platinum to make that compound? Your turn. All right, my turn. And if you look at the product, what's different? Ooh, nitrogen. It's an amine, but it's a primary amine. And what that means is, well, it's a lot of means in my vocabulary now. Ooh, that was awful. Primary amine, which I can also write like this. What do you react with hydrogen and a catalyst? Remember, the catalyst can be nickel, platinum, like in our case, or palladium. You start with a nitrile. And the carbon here or here is, oops, I don't have a nitrile. Oh no, I had carbon on the brain. That's right. You start with a nitrile. And this carbon bonded to the NH2 becomes this one. Therefore, that's this carbon. This is my R group. Therefore, I have my R group and then my nitrile, which includes that carbon. And notice I'm not adding any carbons. I end up with 4 carbons. Guess what? I started with 4 carbons. And that's how you do it. All right, let's continue on. Now, for this slide, click switches off, but it's important background information. Ammonia is a base. Remember, a base is a proton acceptor. And I really should have it like this as an equilibrium with a little arrow going back, meaning it doesn't. Excuse me. If you take ammonia and put it in water, you'll form ammonium hydroxide, acid-base reaction. Well, guess what? Amines are bases too. And you can form what's called an amine salt. Those are ionic compounds formed from the non-bonding nitrogen electrons and another chemical, an acid. Now, I have acid chloride, but let's take that out. And this will occur with all amines except quaternary ammonium salts. Let me show you a better way, now that I know better, to teach this reaction, general reaction. If you look on the whiteboard, I have a way of writing either a primary, secondary, tertiary amine. If R prime and R double prime can either one or both be hydrogen, what I've written here is either a primary, secondary, and tertiary amine. And if I react it with an acid, and let's just stick to the hydrohalogen acids, you have, remember, X here can be chlorine, bromine, or iodide. There are a lot of other examples, but for this class, I'll stick to this. And what you get, what's attached to the nitrogen, stays attached to the nitrogen, and you'll get a hydrogen on there. Hold on. This will become plus, and all molecules have a net zero charge, so you'll have a halogen anion. And I talked earlier that amine salts, their nomenclature is the same as quaternary ammonium salts, but and that is name each R group. name each R group as the alkyl group it is in front, and then add at the end ammonium halide. And remember, chlorine is chloride, Cl chloride, Cl minus chloride, Br minus bromide, I minus iodine. And I went through that with quaternary ammonium salts. Now, when I do this, students in a class will ask me, well, how do you know if you have an amine salt or a quaternary ammonium salt? And I say very simple. Amine salts have 1, 2, or 3 R groups. Quaternary ammonium salts have to have 4. That's why it's called quaternary, for quatern 4. All right, let's look at this reaction again. Any amine with acid will give you an amine salt. And if we react this with, and I can put it up on the arrow, or I can sometimes, any organic chemist would do this. These are both the same reaction, just different ways of writing it. And if we look here, what do we have here? Ooh, an amine. And here, I can write an amine like this. R prime and R double prime can be hydrogen, and in our case, they are. And I'll call this R. And when you react it, notice here, HX, X can be chlorine, in our case, it's bromine, or iodine. Proton transfer to form a salt, an amine salt in this case. And in our case, what's R? Ethyl. Now, nitrogen already has 2 hydrogens, R prime and R double prime. And I could put it on here like this. And then I'm going to add this third one like this, plus charge, and then the anion would be bromine. Now, you could also have written it this way. One, two, 3 hydrogens. You don't have to put charges, I always will. And that's the same molecule. These two are the same, just different ways of writing it. What you're doing is condensing the hydrogens on the nitrogen in the top. All right, your turn to have some fun. Your turn. Give the organic product or products are the following, and I'm about to sneeze, so I'm going to turn off everything. I'm back. And I think everybody's done, so it's my turn. What's different? Ooh, what's not carbon? What's not hydrogen? Nitrogen. We have an amine. which any amine, and I'm doing that as soon as I see the acid, HCl, where R prime and R double prime can be hydrogen. In our case, they are. And what you get, acid-base reaction, proton transfer to form this amine salt. You don't have to put down the charges, but I do. And it has an anion because all molecules have a net zero charge. What's our isopropyl? Therefore, I don't break carbon-carbon single bonds. It has two hydrogens. I'm going to add another one, plus charge. My anion is chloride. Put in my hydrogens. And you could have also drawn it this way. My R group is still isopropyl. Notice 1, 2, 3. Hydrogens on nitrogen, drop that way. Either one would be correct. Oh, let's do one more. And there you go. One more to do. Give the organic product or products for the following. And it's my turn. And what's different? What's not carbon? What's not hydrogen? A nitrogen with two R groups on it. This is a secondary amine, but it's an amine which, because I'm reacting with HX, hydrogen iodide is an acid, I'll write it this way, where R prime and R double prime, one or both, can be hydrogen. In this case, I'll call the methyl groups, two of them, R and R prime, and the hydrogen R double prime. And we're reacting with HX. X equals chlorine, bromine, or iodide. And this is a straight acid-base proton transfer. What's attached to the nitrogen stays attached, gets one more hydrogen, it's got a positive charge. The halogen on the HX becomes this anion. And now we can go ahead. What's attached to nitrogen, and I'll write it this way. R prime and R double prime are still there, or R and R prime. R double prime is a hydrogen. We'll add one more hydrogen. And, oops. And our X is iodine. And you could have also written it this way. And there's a third way, which I won't write, having each methyl group on the nitrogen. Notice one hydrogen plus one is 2. In amine salts, there's 4 bonds, including the hydrogens. To nitrogen, just like a quaternary ammonium salt, but one of the bonds is always going to be at least a hydrogen. And that's how you make it. By the way, that would be called dimethyl ammonium iodide. But I'll never combine synthesis and nomenclature. I had that when I was an undergrad. Oh, that was rough. And that's an important reaction. How important? Some of the drugs you take are amines. And when they get in your stomach with HCl, the acid in your stomach, they form amine salts, and that makes them more soluble in the water in your stomach and your blood. Mother Nature does amazing things. All right, guess what time it is? Well, if I look at the clock, you're going to have to wait 5 minutes to find out what time it really is. And time for a 5-minute break. I'm going to get up and stretch. I'll see you in 5 minutes. And I've made you wait a whole 5 minutes to figure out, guess what time it is? It's new functional group time. And we're going to talk about a new functional group that contains nitrogen. And that new functional group is the amide. Everybody see that on their screen? And an amide, I have a fancy way of drawing it, is carbonyl with an R group and a nitrogen. And nitrogen in amides can have 3 bonds to it. And it could have R prime and R double prime. Now, R prime and R double prime, one or both or none, can be hydrogen. And this is an amide. And I should tell you one, I worked for a company, Axo, that made amides. In fact, I came up with a high purity amide that they're still selling, I developed. And I will teach you or tell you this chapter or this area about one of the dumbest things I've ever done. And luckily, because I'm an organic chemist and also a surfactant chemist, I was able to get out of the dangerous situation that I did to myself that was beyond dumb, like really dumb. All right, now skip the next slide. There's different types of primary. I'll do this real quick. A primary amide, and I'll never ask that on a test. Both our groups are hydrogen, our prime and our double prime. Secondary, there's a hydrogen and our prime, and tertiary, and switches totally off for what I'm doing now. Both our prime and our double prime are not hydrogens. So that's primary, secondary, tertiary amide, but we won't use that. Now, switch is still off, but for some reason, like esters, when you have a cyclic amide, which you can, notice the nitrogen is attached to the carbonyl here. And this is where these two are connected in the ring. It's called a lactam. And that will never be on a test. But if you have it in other classes, and they can say, well, didn't Dr. White talk about it? Well, I did. All right, now, turns out when we have an amide, both R prime, and R double prime, in one very special case, can be, or R and R prime can be hydrogen, and R can be ammonia. And I'll write it like this. And here my R of the amide is NH2. And this is called urea. And urea at room temperature is a white powdered solid that's highly soluble in water. And it's the major organic molecule or chemical in urine. And that's one way your body gets rid of nitrogen waste, by eliminating urea. Now, urea itself reacts like amides, and I've used it when to make certain polymers. And I'll talk about more about urea when we get into polymers. Now, time to learn about something dumb Dr. White did. Yes, I can do dumb things. Does everybody see on your screen capsaicin? And this is a molecule. This is a common name, not the IUPAC. And notice right here, I have an amide. I also have an ether. I have an alcohol. I have a benzene ring. and switches totally off for this, and you got a double bond. There's a lot going on in that molecule. Now, how many of you have ever had hot peppers? And you know, when you eat them, you get that burn, and you also get that what endorphin rush in your brain that heats it up here. Well, what makes peppers hot? Capsaicin. The more in a pepper you have, the hotter it is. Whether you're talking about jalapeno peppers, habanero peppers, ghost peppers, which are now we're getting pretty hot, the amount of capsaicin in there determines how hot a pepper is. There's very little, not much heat. There's a lot, it kicks a wallop. Now, here's the dumbest thing I've ever done in my life. Not the dumbest, but it comes up pretty close. Let's see. Now, a place that I like to buy things from is called the Spice House. And a number of years ago, I happened, this is back when I went to their store in Evanston. Now I'm too lazy with the pandemic, and also it's a 2 hour, almost a 2 hour round trip. I just ordered online. At that time, they didn't have online, so you had to go there. They came out with a new product years ago, and it was ground habanero chilies. So I bought a small jar. Wow, the prices have gone up, but it's worth it. And I came home and you see this nice brown powder. Well, I wonder how hot it is. Well, here's the dumb thing I did. Are you ready for this? I took off the cap, it had paper underneath. You take it, you know, it had a powder type shape. I went, I wonder how hot it is. And as soon as I did that, I realized wrong, real wrong. Like my tongue, the inner part of my lips were not hot, they were in pain. And I'm thinking I better get myself to a emergency room. It was that bad. But luckily, I'm an organic chemist who knows organic chemistry in the real world. And I'll teach you this later on. There's a principle called like dissolves like. Things that are polar are polar and solid, soluble and polar things. Things that are non-polar are soluble and non-polar things. You mix two together, they're not soluble. Now, if you look at capsaicin right here, this is non-polar. Therefore, if my mouth is on and tongue is on fire and in pain, water will do nothing because of like dissolve like. And if you've ever been to a restaurant where somebody eats some hot peppers, like a Chinese restaurant, you tell them don't eat the peppers and they do and they're in pain, they'll bring them some milk. Why? Not because of the water in the milk, because there's fat in the milk, which is non-polar and helps get it out. Fat and vegetable oil are non-polar. And as soon as I realized water ain't going to do nothing for my pain, I was standing right by my refrigerator when this happened. I opened up the refrigerator, grabbed a bottle of mayonnaise, got a spoon, went to the sink, mayonnaise in the mouth, swished it around like mouthwash, spit it out, did it a second time, everything was gone. And that's because like dissolves like. Now, how many of you have ever been in a place where they sell very hot chicken, the buffalo wings? And what do they normally give you with that? Celery. And what's in with the celery?
Ranch.
Ranch. And what's a major component of ranch? Oil, vegetable oil, or fat. And if your mouth is hot, you take some of the celery sticks, put it in a ranch and eat it. And that gets that off your skin. And that's why they do that. And if you've ever been in a restaurant also, I've seen this too, where somebody's in pain from eating hot peppers. they give them bread and butter or crackers and butter. Why? Well, it's a way of getting butter, fat into your mouth to get the capsaicin out of the pain things. Now, that habanero powder I still buy. I'm just very careful with it. In a pot of, say, a 4 or 5 quart pot of chili, just 1 or 2 or 3 taps, and it gives a real nice floral, I don't know if that's the right way to describe it, really nice taste with some heat. Not heat to knock your socks off, but nice heat. So you got to be careful of habanero. And I think now they sell ghost powder. They've got a lot, let's see. Yep, they got ghost peppers, so that means they probably have ghost pepper powder, which is even more dangerous than a habanero. But anyways, if you ever need spices, and I've talked about this before, you should go to the spice house. All right. Now you learned about something stupid, and boy, was that stupid. Now I'm really careful around hot powdered peppers, especially from the spice house. All right, now the next slide, how do you make an amide? I'm going to combine 2 slides, this one and the next one, because after I made this, I realized there's a better way of doing this. So let's look at the better way of doing this. And I hope you enjoyed that Dr. White story, which was true and painful. I take a carboxylic acid, react it with this. And what is this? It can be ammonia when R prime and R double prime can be hydrogen, either one or both. That was the first slide. That would be ammonia, or it can be a primary or secondary amine. And when you react that, you'll form an amide. And I worked for a company that did this reaction. Not today, but maybe Monday I'll give you a nice story. Speaking about not stories, but something. If anybody, if you're in my class, know why Monday's lecture is so popular with over 122 views, and I don't have 122 people in my class, let me know. If you're not in my class and you like that video, write a comment in the video. Let me know why you liked it, why it's so popular. All right, let's do this. And if we look at the following, the question is, what's the organic product or products for the following? And if we look at this, what's different? The first one, ooh, 2 oxygens, carbonyl with the hydroxy group carbons, that's a carboxylic acid. What's different? The second, ooh, a nitrogen, that's an amine. But I can write it this way, where R prime and R double prime can be hydrogen. And when you react those two together, you form an amide. What's attached to the carbonyl? Carbon, R is still there. The R prime and R double prime are still on the nitrogen. In amide, nitrogen has 3 bonds to it. In an amide, nitrogen has 3 bonds to it. Now, what I didn't show here, you also get water, but that's inorganic. All right, so if we look here, this is R. I can call this R prime, and one of the hydrogens here are double prime. So I'm going to have my carbonyl, nitrogen. What's R? Methyl. What's R prime? Ethyl. Doesn't matter which side, top or bottom. Down here, over here, you put the ethyl. Either one would be correct, and then R double prime hydrogen. Now you could also write it like this. And these are both the same. And that's how you make an amide. And now I'm going to share the fun. And there you go. Have some fun. And in real life, you heat this up with a catalyst, but I'm not going to talk about the catalyst. Some companies use, some don't. And I can't because it's a trade secret, and then my non-disclosure agreements are still in effect with that company. I see everybody's done. And if we look at this, we have what? What's different? What's not carbon? What's not hydrogen? Ooh, two oxygens, the same carbon with carbons, carboxylic acid. Again, look for what's not carbon or hydrogen. Ooh, a nitrogen with carbons here, here, and a hydrogen. That's an amine, which I can draw like this. And R prime and R double prime can, but do not have to be, can be hydrogen. In this case, they're not. And what happens? You form an amide. You get water too, but that's inorganic. And this is R. One of these, and it doesn't matter. You can call R prime, and the other one R double prime. So now I have my R group, my carbonyl, my nitrogen, and R prime is methyl. R double prime is ethyl. Now you could have these switch. I could put the ethyl here and the methyl there. Doesn't matter which. And I know there are 4 bonds to carbon, so I can put in the rest. And that's how you make an amide. Oh, let's have another one. And here's that other one. Your turn. By the way, I don't think we'll have time today, but someone remind me on Monday to tell my amide story. It's interesting. So interesting to see how bullheaded some people can be, not Dr. White, others. All right, my turn. And if we look at this, what's different? What's not carbon? What's not hydrogen? Ooh, oxygens to carbon with carbons on it, a carboxylic acid. Now here I have nitrogen with 3 hydrogens, ammonia, but I could write it this way. And this is why I said skip the first slide. where R prime and R double prime can be hydrogen. So in that case, what happens? You form an amide. And here, what's our isopropyl? What's our prime and our double prime? Hydrogens, which they can be, and in our case, they are. So I'll have my R group, my carbonyl, my nitrogen, and you can write it this way. And there's our amide, or let me move our video pictures over here so I have more room. You can also write it this way. And either one would be correct, and that's an amide. But I do have time for a real quick story. When this type of amide, when these are very long, about 20 carbons or 22, it's been a while, hold on one second. "22 carbons, including the carbonyl." I was right. It's called a rusamide. And the R group is very long. As you see in this picture right here, a lot of carbons. Every bend of the line is a carbon. Now, I work for a company that made a rusamide. I don't have time today to tell the whole story, but a rusamide is called a slip reagent. And a slip reagent is used in making plastic bags. Do I have one here? Yes, I do. All right, I just happen to have one over here, a baggie. And you notice how you can open it up and the plastic here doesn't stick together. It slips apart easily. That's because there's a rusamide in here and it's a fatty feel to it. It makes things slip apart. Now, I'm probably one of the only ones in Northern Illinois or the United States who does this. Only if you ever go into the supermarket, into the vegetable area, and you pull one of those bags off the roll to put your vegetables in, and you try to open it up and it won't open up. And the reason it won't open up is because of van der Waals forces, and the company that made that was too cheap to put enough rusamide in there so it slips apart and you can open it up. As soon as I pull a bag off a roll, or when they made it, somebody messed up and didn't put enough rusamide in there like they should have, one of those two things. And if I take it off a roll and after 2 tries, I can't open it up, I know why, and I'll find another roll where they did it correctly. I'm not going to spend the next 10 minutes trying to pull it apart because there's not enough rusamide. All right. If I look at the clock, which I just did, it's laboratory time. So I better open up the lab. All right, everybody see carboxylic acids lab on the screen? Thank you. All right, now, as I said, when I developed these labs years ago, when I inherited Chem 170, and the labs they were doing were beyond awful. They really were awful, awful, awful. I came up and made up my own labs because of the time frame when we're face to face. Most schools, you have 3 hours or 2 hours and 50 minutes. at ECC for this course, you only have an hour and 50 minutes. Well, that really causes some difficulties because you can't use traditional lab books for this course because they're based on 2.5-hour labs approximately or longer. So I came up with certain concepts to teach people like you about functional groups. And for carboxylic acids, remember, what is a carboxylic acid? This. And the first thing is, what's the solubility in water? And here you take some test tubes, fill them about halfway with water, put in each of the following chemicals, carboxylic acids, and see if they're soluble. Shake it up or use the vibro mixer. You get one layer. Is it homogeneous, or do you have two separate layers? And what I don't have here, which I normally do and I forgot to put on here, underneath where it says acetic acid, propanoic acid, and stearic and oleic, draw the structures. And you can find stearic and oleic acid if you use my favorite search engine, Google. And because of the generation gap, I try never to use Google as a verb. I use it as a noun. Ooh, I got some English in my class. Well, anyways, if you did this in a lab, you'd find acetic acid and propanoic acid is soluble, but stearic and oleic are insoluble. I will give you a little hint. Consider how big R is and the solubility. And that's a various structure effect. All right, let's move on. Let's do the reaction of carboxylic acid with sodium hydroxide, not sodium hydroxide, sodium bicarbonate. And here I tell students, we're going to use some real dangerous chemicals in this part, like lemon juice, tomato paste, that's real dangerous, stearic and oleic acids. And let me remind you, the chemical reaction you will be investigating is a carboxylic acid plus sodium bicarbonate, and we'll do that in water. And remember, the general reaction is CO2 carboxylate anion, CO2 given off as a gas, and water. Now, one of the things I have students do is measure with pH paper the initial pH and the final pH. And in case you forgot, pH scale goes from 0 to 14. 7 is neutral pH. Above 7 is basic solution, and below 7 is acidic. And if you add a base, you'd expect the pH to increase. And I tell students, this is a lab you find out, is Dr. White lying to you or not? I'm not, but they find out that. And what you'll be doing is in a beaker, it's easier to clean out than a test tube. You'll add about 10 milliliters of water, about 1 or 2 milliliters of the material if it's a liquid, or about 3 grams if it's a paste or solid, into a beaker. You mix it, use the pH paper to measure it, then add some sodium bicarbonate. Just add a big dollop, and you observe it, and you measure the pH. And notice, what do we see? Bubbles. And what are those bubbles? The carbon dioxide, CO2 given off as a gas. And here's some YouTube videos I didn't ask you to watch. Now, the last one is, and here we're really not doing stearic acid. I should have taken that out. Is the reaction of acetic acid and stearic acid with different compounds. And let's look at it. In each case, you're going to do this in an Erlenmeyer flask. You'll add 20 milliliters of water, about a half milliliter of the carboxylic acid, and some phenolphthalein indicator. Phenolphthalein indicator changes color. When it's acidic, it's clear. When it's basic, it's a wine color. And what you'll do is add enough sodium hydroxide to the mixture of carboxylic acid, one Erlenmeyer acetic, the other oleic acid, and you'll swirl it and let it sit for a little while. And then you'll add 10 more drops to make sure it's really basic. Then after that, you'll add magnesium sulfate and you'll observe it. Now, let me show you the chemistry involved. Oops. Promise I wouldn't do that shorthand. Since I've worked in carboxylic acids in the industrial world, we do shorthand. But anyways, this is a base. Remember, carboxylic acid plus MOH, and what you'll get, the first reaction is the carboxylate anion. Now, the second part, where you take this and watch closely, this is one of the rare times I'm going to balance the chemical reaction. The students get upset if I don't, and I don't want to upset students. It's not fun. And what you get is ion transfer. Magnesium is +2 cation and magnesium sulfate. And here's what you get. This magnesium carboxylate anion. Now notice what's happened. Here has a certain molecular weight, and here essentially it's 2 times the molecular weight in this whole molecule. It's heavier. And what you're going to investigate is what effect does R have on this molecule here being soluble in water. And if you were in the lab, you would find out when you do the final step with the sodium hydroxide soap, it's called, and the magnesium sulfate, acetic acid solution is clear and homogeneous. It did react though, but the oleic acid, after you react with first base and then the magnesium sulfate, it forms a white solid on the inside of the Erlenmeyer. And while you're doing, let's take a look at this video. We've got time. Yeah, we got time. I don't have anything to do till midnight. Not. All right, time out
Drinking
for
warm water
commercial.
before bed erases years of doubt.
Hold on, let me get rid of something.
Jason Anglin with Tri-County Water Conditioning out of Hutchinson and Prior Lake. And here today just to show you the difference that hard water and soft water have on.
Everybody see that YouTube on your screen now?
So what we're gonna do here today is just add 3 drops of just pure soap solution, so it doesn't have all the additives that you'd see at a retail
That's your
store.
sodium
add 3 drops
carboxylate.
to the hard water beaker here. And then we're gonna add 3 drops to the soft water beaker here. And what I'm gonna do is just mimic basically a washing machine, and we're gonna shake these 2 up. Hard water first. You can hear the 18 grains hardness we have in Prior Lake water. So not much effect on the 3 drops of soap solution we added here. Here's the soft water. Much different sound, not nearly as loud. You can see all the suds that we're getting
Now,
for that one. And if we even add another 6 drops to the hard water, we'll just see if we get any more effect.
that's
Just
the
kinda
same
showing
as
you
the
the
sodium
savings
carboxylate.
you're gonna get having soft water as opposed to hard water. Because your soap solutions are basically fighting the hard water, and you're not getting any results from that. We got a little bit here, but it slowly dissipates down. We kind of zoom in a little bit on the.
Now, if you see on the beaker here in our lab, it's much more pronounced. You see this white solid right up there forming? Well, hard water has a lot of ions in it. In our water, it's calcium, but for the lab, it's easier to dissolve magnesium sulfate, make a solution for students to use, than calcium sulfate, a lot harder. But anyways, that's also known as soap scum. And what you made in that last step with the oleic acid, that white solid, I'd be going around to the students saying, you know what that is in your beaker? And they'd say, no. I say, that's soap scum, like in your bathtub. And later on, when we get into fats and oils, I will teach you how to remove that from the wall of a bathtub or a shower in about 3 minutes or less with almost no scrubbing. That's probably the one thing I hate the most cleaning in my house is a bathtub. And I'll teach you later on that years ago, I finally said, why am I spending 45 minutes cleaning my bathtub? Because I hate it too much. I always let it go too long, or I finally have to clean it. I say, you're an organic chemist. How do you clean that off easily? And I thought about it and I said, all right, this is how you do it. And guess what? It is. And I'll teach you, you got to wait until we get into fats and oils to learn that. And with that, here are the different questions. Now, look at part 3. Question from part 3. Write each reaction of the 4 experiments you conducted. And then what did you learn about the relationship of carboxylic acids that you tested and their reaction with sodium hydroxide solution and with magnesium sulfate and their solubility in water? And molecular weight, I do that face to face. And what 4 reactions are there? First, acetic acid with sodium hydroxide, and then that product of sodium hydroxide and acetic acid with magnesium sulfate. Next, that was 2 reactions. Number 3, oleic acid with sodium hydroxide, and then that product with the magnesium sulfate. Essentially, these 2 reactions where R is either for acetic acid or R is for oleic acid. Everybody get that down? Because most people don't do it. I mark it wrong and take off 1,000,000 points. That would hurt your grade too. Anyways, I do take off points if you don't do that. And with that, I'm done for today. I'm done for the week, except for our office hour, or if you email me, All right, important announcement. Monday, I'll have an important announcement that you should have to wait till Monday. So make sure either you come to class Monday or you watch the video Monday, because it's going to be a really important announcement. It's a good announcement, but it's important. And with that, unless you're going to come and stop by and say hello tonight, or you need help, my office hour from 6 to 7:15 on Zoom, a different login, which you have. I'm done for today, and I'll say, have a nice day, have a nice rest of the week. Gang gesund. Bye now.